Hello everyone, and welcome to the second episode of the webinar series about PSA measurements, the parameters awaken reproducing particle size results. I'm Georgia, and today I will present you the custom analysis mode and the additional parameters that the Calliope software makes available for data analysis and post-processing. The following points will be discussed during this webinar. Why do I need the advanced parameters? How do I assess the advanced parameters? Most use advanced parameters and parameters for advanced users. Let's start with the first main question. Why do I need advanced parameters? The advanced parameters could be helpful whenever you are asked to compare our PSA with other particle sizing techniques, and the adjustment of dispersion parameters alone was not sufficient. You can also use the advanced parameters for reproducing competitor data. The first step in case of reproducibility issue is always the adjustment of dispersion parameters. But if this is not enough, advanced parameters can be applied. Be aware that laser diffraction instruments have a low reproducibility, not only due to differences in procedures for sampling or dispersion, but also due to differences between the algorithms which convert the intensity signal into the particle size distribution. The advanced parameters should never be considered the first choice. The first step is trying always to improve the dispersion, starting from the obscuration and then optimizing the settings for liquid and dry dispersion. If the measurement is successful, particles should deagglomerate and not break. At this purpose, the repeatability is a good control parameter. If you haven't done it yet, take once the time to listen to the webinar, Episode 1, Attack of the Particles, because it contains detailed information about this topic. Moreover, we recently published on the extranet an updated version of the application report about sample preparation and sample dispersion, where you will find the same contents of the first webinar. Each particle sizing technique has its own physical principle at the base. Therefore, most of the time there will be a certain difference in the results. Behind this difference, there is always a reasonable explanation that has to be searched in the way how the instrument measures the particle size and which aspect of the particles considers. An old technique, which is still used today, is the sedimentation or pipette method. In case of particles smaller than 10 micrometer, sedimentation technique will measure a higher percentage of particles than laser diffraction. In the cumulative distribution presented in the slide here, you can see how laser diffraction will measure 10% of particles smaller than 10 micrometer, while the sedimentation will measure 30%. This is the case of small and irregular shaped particles like clay in the soil. They have a plateau or tubular shape and they behave similar to the ellipse shown in the picture. During the settling, they orient with the maximum cross-sectional area perpendicular to the direction of the motion. Since according to the Stokes law, the diameter is proportional to the settling velocity, by decreasing the settling velocity, also the diameter will decrease. Therefore, many smaller particles will be measured. Sieving is another very traditional technique, but still very used. In this technique, the particles are considered bidimensional, and they will orient themselves to pass through the mesh opening with the smallest second dimension. For this reason, the sieving D values will be typically smaller than the laser diffraction D values. This is displayed on the right in the exemplary particle size distribution for ground coffee. The gray curve represents the sieving result, and the red curve the laser diffraction result. At each point of the cumulative, the particle diameter measured by sieving is always smaller, as you can see in the D10, D50, and D90 values. However, The advanced parameters allow sometimes to smooth the differences between particle sizing techniques. In this way, users which are working since many years with old technologies can realize that they get comparable results also with more modern techniques which are faster, less time-consuming, and more repeatable. In this slide, you can see a comparison between laser diffraction, sieving, and optical microscopy. By sieving the sample at 30 micrometer, the particles are passing through the mesh with the smallest side. This means that the measured particle size will be smaller than 30 micrometer, although the image from the microscope shows us that the particle measure around 50 micrometer, sorry. And also in this laser diffraction result, the peak goes behind 30 micrometer. Typically, in a dispersion, you have a mixture of particles with a similar size but different shape. Let's assume this will look like the one in the slide. If we take the following particle, a different diffraction center could be chosen. If one single diffraction center, like the green circle, is chosen, the reported particle size would be monodispersed because one single particle size would be detected. However, on the same particle, there are different edges which can act like diffraction centers. In this case, the reported particle size distribution will be polydispersed. Because it's like particles or different sizes will be detected. The dispersion makes also the difference. A good dispersion will give a particle size distribution like the light blue one, which is polydispersed, while a bad dispersion could give a particle size distribution like the green one, which is monodispersed. This relativity of laser diffraction is in particular true for irregular shaped particles. You should know from the training that the proportion of each size class is calculated by the software which compares measured data with theoretical expected values for different sizes. The algorithm finds the best fit between the measured and theoretical values and gives a result, the particle size distribution. This means that the theoretical values are always the one obtained by using me and Fraunhofer. But the algorithm which is used to find the best fit is different. Each instrument is compliant to the ISO norm 13320. The norm was developed in 2009 in order to make the measurement results of laser diffraction instruments comparable. It also specifies in detail which properties a powder must have to prove the accuracy of an instrument. For instance, it says that triple certified reference materials are required. The particles have to be spherical and the particle size distribution must be broad enough, which means that the ratio between the D90 and D10 must be at least a value of 1.5. As a result of this regulation, each algorithm is able to calculate in a highly comparable way the particle size of spherical standard particles. However, in case of non-spherical irregular shaped particles, the existing difference between the algorithms can determine also different results. In this slide, I show you the difference between two laser diffraction instruments can be reduced by using the advanced parameters. We measure the sample in our PSA and in a competitor instrument. The green curve displays the result of the PSA without any adjustment. The yellow curve, the result obtained with the competitor instrument. And the red curve represents the result of the PSA after adjustment. You can see how, after adjustments, the results come closer to the ones of the competitor. The yellow and the red curves are almost overlapping. By adjusting the right advanced parameters, no change within the algorithm is done. It's just a matter of data post-processing. And Always remember that basic theory of laser diffraction is the same, but each instrument works with a different algorithm. My colleague Natalie found this sketch of Eddie Heiser on YouTube. Take once the time to see the video, which is very fun and fits perfectly in this context. There is also the link to the YouTube video. In our case, this is simply to underline that as long as you know what you're doing and you can justify your choice, it's fine. Moreover, the use of advanced parameters is common in the world of laser diffraction, where actually the main goal is data consistency in quality control and get comparable results between instruments of different generation. What is important to know for you is that all of the following information is based on the advanced parameters provided by SILAS in SizeExpert. By using Calliope 2.10 or a higher version, some of them might become obsolete. You can have access to the advanced parameters already before the measurement. In the section Analysis Mode, you can select Custom Mode. Through this, you will have access to all available advanced parameters. You can also apply the advanced parameters after the measurement by using the recalculation function. A long list of parameters is available in the software. However, you won't need to use them all. There are some most common used advanced parameters, and in this webinar, I will focus on them. The simplest division is between global and range-specific parameters. We call global all parameters for which the change is valid over the full calibration range. And these are translation, width, diameter switching point, monohisto option. For the range-specific, the change is valid only in the chosen range. Smoothing value, high curve value, and low curve value belong to this group. As you may know, our PSA instrument requires a precise calibration, which is done on every new instrument before it leaves the factory. Two size ranges are considered for the calibration. Range 1, which includes particles smaller than 10 micrometer, and range 2, which actually covers the whole size range. Calypso 1 is used for the calibration of range 1, while Calypso 2 and PS 226 for range 2. According to the size, the algorithm will choose to calculate the particle size distribution by using the calibration for range 1 or the calibration for range 2. 10 micrometer represents exactly the default particle size at which the software switches from range 1 to range 2. Let's start the section of global parameters. The width applies a compression factor to the histogram, therefore the distribution becomes narrower or broader. D10 and D90 are most affected, and in case of correlation with competitor results or other laser diffraction instruments, the D10 and D90 can be modified by moving the width without changing the D50. Default value is 0, minimum applicable value is -2, the maximum one is +2. First example you see is glass beads with size range between 3-30 micrometer. It was measured in liquid mode and the width was not changed. The measured D10 was 9 micrometer, the D50 15.3, and the D90 was 26. The same sample was measured at different positive width values without changing the translation, which is always 1, default value. You can read in the table how the D10 and the D90 change. D10 is increasing, D90 is decreasing at the same time, while the D50 is constant. This means that the particle size distribution is becoming narrow. In the following slide, the effects of negative width values on the same sample are presented. And by decreasing the width, the D10 and D90 change as well. The D10 in this case is decreasing, while the D90 is increasing. It can be noted that at very negative values like -1, the D50 is also affected, and the particle size distribution becomes not meaningful anymore. Consider that D50 remains stable for moderately negative values, but distribution becomes bimodal at highly negative values, where D50 is strongly affected. The width or broadening function should be therefore used very carefully. Below the width in the same window, you will find the translation. This option will shift the whole distribution towards smaller or larger size range. The change of d-values is linear. Default value is 1, and it can reach a minimum of 0.1 and a maximum of 2. We tested the effect of translation on a sample of aluminum hydroxide. The green curve in the middle is the particle size distribution measured at translation 1, which is the default value. The yellow one was measured with low translation at 0.5, and the red one with high translation value 2. From the distribution and the table, you can see how by decreasing the translation, all d-values will decrease, while by increasing it, the d-values increase as well. This parameter could be useful in case of comparison with sieving. Another interesting parameter is the diameter switching point. It is the diameter at which the algorithm switches between the first and the second calibration range. The algorithm will use the calibration for range 1 if the D98 is smaller than the diameter switching point. It will use the calibration for range 2 if the D98 is bigger than the diameter switching point. Default value is 10, while minimum applicable value is 0.04 and the maximum one is 500 micrometer. The software won't tell you if you're measuring a range 1 or range 2. Therefore, you have to check the D98 on the cumulative curve. Default value for diameter switching point is 10 micrometer. As you can see in the cumulative distribution displayed in green, the D98 is actually bigger than the diameter switching point, so than 10. This means that the calibration for range 2 has been chosen by the algorithm. In the case the particles you want to measure are in the range below 10 micrometer, the calibration for range 1 would be more accurate. However, when the expected D98 is close to the diameter switching point, like in this case, the algorithm could choose the wrong calibration range. To avoid this and to be sure to measure in range 1, you can change the diameter switching point by moving it away from 10 micrometer. In fact, we increase the diameter switching point to 20, and in this way the calibration for range 1 is used. The D98 of the new yellow cumulative, calculated with the calibration for range 1, is in fact now 10, which is smaller than the diameter switching point, 20. A sample of alumina powder was measured at diameter switching point of 10, 15, and 20. As you can see in the distribution and in the table, there is a significant difference between 10 and the other two values, but the results with diameter switching point 15 and 20 are the same. This function can be used in case of unexpected shoulders in a distribution which was supposed to be monodisperse, or if you are measuring particles smaller than 10 micrometer and want to make sure that range 1 is used. In this case, you can increase the diameter switching point. Among the global parameters, you find the monohisto option. It reduces the minor peaks and narrows the distribution. The D10 and D90 are mostly affected, And it's useful when you are sure that the particle size distribution should be monodispersed, because this function will eliminate any potential contaminants. In the following slide is shown an example result for glass beads with size range between 10 and 100 micrometer. We know that this standard should be monodispersed and only one population should be measured. Without monohisto option, you see minor inconsistent thinness beside the peak. The measure D10 is 25, D50 47, and D90 is 78 micrometer. Most probably, there is dust contamination, which increases the broadness of the distribution, which has a span bigger than 1, and decreases the D10, which becomes too small. When the monohisto option is applied, the small thinness are not visible anymore. The D10 is now in the certified range, the span becomes smaller than 1, and no more contaminants are visible. Let's move now to the range-specific parameters. This can be changed separately and independently for each calibration range. The smoothing factor is applied to the curve by the algorithm. In the software, you can choose between automatic and custom mode. In the automatic mode, the smoothing for the curve will be determined by the algorithm to minimize the fit to error between measured and theoretical data. In custom mode, the smoothing values can be entered manually for range 1 and range 2. Minimum applicable value is 0.001, maximum is 1000. In the next 3 slides, I will show you what happens by changing the smoothing values from low to high. We measured quartz powder in dry mode with low smoothing of 0.02. A repetition of 4 measurements was performed for this sample, and you can see in the table that the repeatability for the D50 is very low, with a relative standard deviation of 18%. The particle size distribution are narrow, but with very sharp and highly defined peaks. So the same sample was measured with a medium smoothing value of 0.6. The measurement was again repeated 4 times. The repeatability for the D50 increases. In fact, the relative standard deviation decreases from 18% to 3.3%. What can be observed in the particle size distribution is that it becomes broader and there are less peaks. However, by increasing the smoothing, at some point, the fit error increases as well. This means that the difference between measured and theoretical data becomes bigger. Therefore, the fit error also increases. For this reason, keep an eye on the fit error by increasing the smoothing. Other 2 useful range-specific parameters are the I-curve and I-curve value. You find them in the section of data limitation. There are 2 options for the I-curve: the I-curve threshold, which is always activated by default, and the I-curve cut, which is very seldom used. In both cases, the I-curve detects and removes the artifacts for the I-curve hand. The I-curve threshold can be applied above a certain value, which is the I-curve value. The same value is actually also used for the I-curve cut. The value you will find in the software by default is 0.85. This means that by looking at the cumulative, the artifacts above the D85 will be smoothed. An example for this is shown in the next slide. In the following slide, 2 exemplary cumulative distributions are displayed. By using the I-curve threshold value of 1, we ask to the software to set to 0 all histogram values above D100 for which the frequency signal is very low. This means that the thinness above 100% are not considered, but actually the maximum limit in the cumulative is exactly 100%. Therefore, in this case, no I-curve threshold is applied along the yellow distribution. By using the ICOV threshold value of 0.85 on a yellow curve, all histogram values above D85 for which the size bins have very low frequency are set to 0. This happens because in this region, a low signal intensity is likely associated to an artifact. The resulting cumulative is the one displayed in green, and the smoothed area on the cumulative is marked with the red circle. To show you more in the specific what happens, we measure the sample of quartz powder. The yellow curve would be the result when ICOV threshold is not applied, the green one when ICOV threshold is applied. What happens in details can be seen in the histogram representation. This is how the histogram looks like when the ICOV threshold is not applied. By applying it, the histograms above D85 with very low frequency are set to 0. As you can read in the table, the D values are slightly affected and the particle size distribution becomes narrower and smoother. By applying the ICOV cut, all histogram values above the high curve value are not set to 0, but they are cut and no extrapolation applies. The high extrapolation is a parameter which I will describe in the next slides. It acts by smoothing the edge of the peak at the bigger sizes end. Therefore, on the cumulative as well as on the density distribution, you will see a significant change in the particle size distribution shape, which has a sharp side and is not anymore a nice bell-shaped curve. In comparison with the ICOV threshold, the D values are strongly affected. Therefore, also these parameters should be used very carefully. Similarly to the high curve, there are two options for the low curve. The low curve threshold, which is always activated by default, and the cut, which is very seldom used. In both cases, the low curve detects and removes the artifacts for the low curve end. As well as for the high curve threshold, there is a low curve value, and below this value applies the low curve. By default, you find 0 in the software. This means that the Wu distribution is taken into account and no smoothing or cut will be applied. 1 micrometer standard sample was measured. The green curve here displayed in the figure is obtained when the low curve threshold is not applied. The yellow curve when the low curve threshold is applied. A low curve value of 0.1 was chosen in this case, and this corresponds to D10. This means that the particle sizes below D10 will be smoothed because all histogram values below D10, for which the size bins have very low frequency, are set to 0. You can read in the table how the D10 is mostly affected and increased. The reason for this is that there is no more the effect of contamination and artifacts in the smaller size range. The particle size distribution becomes narrow and slightly shifts towards larger size ranges. In the slide are displayed the results for the 1 micrometer standard when the low curve cut is not applied and when it's applied. Between low curve threshold and low curve cut, there is a small difference, not only in the D values, but also in the particle size distribution. However, what can be noted is that when the cut is applied, you see this in the red curve, the lower edge of the curve is not smoothed. It's not smoothed like in the threshold, which is the yellow curve, and looks sharper. In fact, the artifacts are not simply smoothed in the case of the cut, but they are really erased. The parameters I've listed so far are the first we consider anytime we have to use the advanced parameters. The one I'm going to describe in the next slides can be used only in case the sample is well known. You know exactly what you are looking for, and you know the instruments you are working with. Among these parameters, you find the cell selection, the signal-to-noise ratio and limit, and the extrapolation functions. In the cell selection window of the software, you find two options, channel limitation and range-specific additional cells. Before starting with the description of the cell selection options, I would like to refresh your mind about the detector geometry and channel numbering. The first rule of laser diffraction is that small particles diffract light at large angles, and large particles diffract light at small diffraction angles. You may all know that in the PSA we have a silicon wedge-shaped detector with 42 physical detectors and an aperture of 1/4 mm, where the undiffracted laser light is passing through. The detectors which are placed at large angles are for the detection of small particles, while the detectors placed at small angles are for the large particles. All 42 elements detect signal from laser 1. For PSA 1090 and 1190, only 17 elements of the 42 are used to detect signal from laser 2. Let's now have a look at the principal detectors inside each PSA series. In the PSA 990, there is the obscuration detector, the wedge detector, and two additional detectors placed at 45 and 30 degrees. If we number the channels in order of increasing detection angles, we have that from 1 to 42 are the channels which detect signals from laser 1. 43 and 44 are the numbers which refer to the additional detectors, which are not on the wedge detector. In total, we have 44 channels or angles. In the PSA 1090, there is a second laser and one more detector at 60 degrees with number 43, which is only detecting signals coming from laser 2. The numbering for the additional cells changes a little for the 1090. The additional detector at 40 degrees has number 44 when detects signal for laser 1, has number 63 when detects signal for laser 2. The one at 30 degrees has number 45 when counts for laser 1 and 64 for laser 2. For this reason, in the PSA 1090, we count 64 channels or angles. In the PSA 1190, there is additionally the CCD camera with its 7 virtual channels. Virtual because they are not on physical detectors. These channels count for particles larger than 500 micrometer. The number is changed again, but the way how the numbers are assigned to the detectors follow the same principle. The additional detector at 45 degrees has number 51 when counts for laser 1 and 70 for laser 2. The one at 30 degrees has number 52 for laser 1 and 71 for laser 2. Therefore, in the PSA 1190, 71 channels or angles are counted in total. Cell selection menu is used to switch off detector channels for specific diffraction angles. The example shown in the slides regards the PSA 1190. You know from the previous slide that actual channels are numbered from 1 to 71. However, by default in the software, it's set from 0 to 72. This is to make sure that all channels are active. Between the lower and upper value, at least 5 channels have to be active. By reducing or restricting the lower channels, you will eliminate the signals for larger particles. By restricting the upper channels, you will eliminate the signals for small particles. In the following slides, it's shown what happens when the lower channels are restricted. We took a sample of aluminium hydroxide. The green curve represents the result when all channels are active. The yellow curve is obtained when the first channel till the sixth are not active. These are exactly the virtual channel of the CCD camera, which detect larger particles. In fact, you can see from the particle size distribution that the air bubble peak at 1000 micrometer disappears. And from the table, you can read that the D values becomes smaller. And the final particle size distribution is also narrower. Let's say now what happens when restricting the upper channels. We measured a sample, used for powder coating. The green curve represents the results when all channels are active. The yellow curve is obtained when the last channels from 50 to 72 are not active. After deactivation, in particular, the D10 increases and the particle size distribution becomes also in this case narrow. The influence of artifacts and contaminants is removed. The additional detectors can also be selectively activated or deactivated. This option is actually valid only when using the Mie approximation because no additional cells are involved in Fraunhofer. The activation is range specific and the cells can be deactivated in case you think that there are inconsistent signals in the small size range. You should start to disable the additional cell at 45 degrees. If not enough, then additionally disable first 30 degrees and then 16 degrees. There are other global parameters which belong to the group of parameters for advanced users. These are signal-to-noise ratio limit and high and phi extrapolation. The signal-to-noise option, like the high curve threshold and the low curve threshold in the data limitation section, yeah, they are in the same window, in the same data limitation window. And in particular, the signal-to-noise limit defines up to which detectors the signal-to-noise ratio rule applies. Default value of 60 means that the rule only applies to the first 16 channels, which are really the small angle detectors for large particles. The signal-to-noise ratio is expressed in percentage and represents the ratio between the signal coming from the sample and the signal measured during the background. If the detected value for a particular detector is lower than this ratio, the channel value is set to 0. Nickel oxide particles were measured in liquid mode. The green curve displays the result when signal-to-noise ratio is 0, while the yellow curve is obtained after increasing the ratio to 5%. The values decrease and the particle size distribution becomes narrow. When the ratio is 0, which is the default value, the signal is always taken into account. This option is mainly used when small particles have to be measured. In fact, by changing the signal-to-noise ratio, you can avoid that the highest scattering intensity of big contaminants will cover the signal of small particles. In contrast to deselecting detectors, here the noisy channels are included, but their values is set to 0. If the signal rises then above the threshold, they will be considered again for the calculation. The last two parameters I will talk about are the high and phi extrapolation. There are also range-specific parameters. High extrapolation is used when large particles have to be favored. Therefore, D90 is mostly affected. It can be activated only when a high curve threshold is selected. It cannot be applied when high curve cat is on. Fine extrapolation is used when small particles have to be favored. In this case, D10 is affected. We tested on the glipizide the effect of high and fine extrapolation. In the picture, The yellow curve refers to the result obtained when high extrapolation is not applied, while the green curve displays the result with high extrapolation applied. The D90 increases from 3 to 4 micrometer, and also in the shape of the particle size distribution there is a smoothing of the curve, which is indicated by the red circle. When fine extrapolation on the same sample is applied, the D10 decreases from 0.9 to 0.8 micrometer, and the curve undergoes the same smoothing effect as in the high extrapolation, but this time on the smaller sizes end. Coming to the conclusion, I would like to underline the most important consideration to do when approaching data processing with the advanced parameters. Advanced parameters are never the first choice. Before using them, make sure that you tried everything to improve the dispersion. Focus on the final goal and change the right advanced parameter. Don't play around with them. Changes have to be done with critical thinking. Understand first what is the problem and think about what could be the reason for that. Especially when you deal with different particle sizing techniques, analyze the difference between the instruments to understand then the results. Additional literature is available in the extranet. In the reference guide, you will find a detailed description of all parameters, not only the ones I have described you in this webinar. Moreover, there is a document in the manual section for the PSA, reproducing particle size results from other instruments with a PSA. And as I told you at the beginning of the webinar, the application report How to Prepare and Disperse Your Sample for Particle Size Measurement by Laser Diffraction has been updated, and also the new version has been published on the extranet. I thank you all for joining the webinar, and I would like to remember you that the webinar will be available in the next few days, always in the extranet, and you can listen it again whenever you want. Now it's time for your questions.